Okay. All right. Thank you all for attending today's seminar. I'm very excited to have this opportunity to talk about the research we have been working here at UBC to the broad audience at the Asia Pacific, as well as global. I think there might also global attendees. So today I'm going to talk about the advanced structure design and emerging application of nanocellulose. A brief outline, including I'll divide today's talk into two parts. So one is hierarchical structure design, briefly talking about the aerogel and as well as 3D printing. Then I will focus on the advanced application for water treatment, antibacterial thermal insulation, as well as ionic conducting hydrogel. So I'm sure most of attendees, you already know what is cellulose and what is nanocellulose, and also the hierarchical structure in the trees. So in a tree, there are a lot of vascular structures. Those vascular structures serve as a conduct for the water uptake and also the nutrient uptake. So depending on the species, there are vessels, there are trichase fibers. So nevertheless, they all have the cell wall. So within the cell wall, there's a lignocellulose matrix as shown here. So which include the lignin, hemicellulose, and as well as cellulose. Those are three major polymer you can find in the fibers. So within the lignocellulose matrix, there's elementary fiber. Elementary fiber is mostly about it's about 36 chains, cellulose chains, that is forming hydrogen bonding with each other to have these elementary fibers. So those elementary fibers are the basic building block for the fibers, cellulose fibers. So it has many advantages. For example, it has very high crystallinity. It has excellent mechanical properties, as well as high surface area, as well as a lot of surface hydroxyl group, which can be used for the modification. So if we look at the elementary fibers, so this is assuming this is elementary fibers, so we see alternating a crystalline region as well as an amorphous region, or we call it disorder region. So by using different ways, so we can get two types of nanocellulose. One is the cellulose nanocrystal, which is basically we remove the disorder region by strong acid hydrolysis, leaving the crystalline region. And those nanocellulose are rod-like, is very high crystallinity, can be over 90%. Another part is if we break the interfiber hydrogen bonding between here, but while keeping the amorphous region and the disorder region, then we can get the long flexible nanofibers. So those flexible nanofiber it has very thin. It can be like a few nanometer in diameter, and also it has very high aspect ratios. So majority of my work here is work on the cellulose nanofibers. I show here the AFM image. So after isolation, the nanocellulose, they are presenting mostly in the aqueous suspension. It looks like transparent. So in the lab, we want to give the transparent suspension into some form, like you can handle, you can see. So this relate to our research on the hierarchical structure design. So we are making, for example, some micron fibers, nanofibers, as well as films. For example, the current pneumatic film or sensor film, as well as some antibacterial films, as well as three-dimensional structure, hydrogel and the aerogel. So very briefly about the aerogel, I think this aerogel has been researched for nanocellulose aerogel has been researched for over a decade. I think the first aerogel paper about nanocellulose probably coming out in the early 2010s. So here's we use ice crystal templating method to assemble those cellulose nanofiber into the honeycomb structure. So after removing the ice crystal, then we can have this beautifully micron-sized honeycomb structure. So we can make this very low density. For example, the density can be as low as 1.7 milligram per cubic centimeter, which is very close to the air. The air density is about 1.3 milligram per cubic centimeter. And this density can be fastly changed by having a different concentration. And then the porosity is very high, it's over 99.5% porosity. So potential application, for example, this is very lightweight. Potential application for this one can be used for the thermal insulation, trying to bring up the laser. Okay. So this video it just shows the lightweight that the aerogel can be attracted by static force between the plastic tube and the aerogel, meaning it's very lightweight. So therefore, it can be useful, for example, aerospace, packaging, thermal insulation. Also, it is super absorbent material. So if you take a piece of this aerogel and you put into a water or any other liquid, it can absorb. It can fully saturate within seconds. For example, it can absorb 210 times of water or 370 times of chloroform because chloroform has much higher density. And then you can easily remove the water by squeezing. And then after squeezing out the water, you can reuse. For example, this is a dyed aerogel. So we squeeze out the water and put back into the water, and then it will recover within 4 seconds. So it should be noted that this aerogel we do 100% cellulose. We do not use any of the chemical cross-linker. So mostly it's by hydrogen bonding. So all those the strong structure is formed by the hydrogen bonding due to the S crystal templating. This is only to the very high surface area of the nanocellular. You could not achieve this by, for example, if you use the pulp fiber, able just very easily scatter once you put into water. But due to the nanocellular very high surface area, a lot of surface function group, carboxyl group, hydroxyl group, then it will be very strong by just by physical cross-linking. So this, and also it shows very good wide resilience. So here's a piece of aerogel. We can compress it in water, and then after releasing the force, it will recover immediately, as you see here. So this is recover to the original state, and it shows very low hysteresis, meaning so this is a super elastic. So this is it can also compress for 100 cycles without losing the property. So this is a 1 cycle to 100 cycle curve. They all show the complete recovery of the aerogel. So this aerogel can be served as a platform for a lot of modification here because we have the aerogel, and then even before going to the aerogel, so for example, we have the hydrogel. So the hydrogel, we can do a lot of solvent exchange to different kind of solvent. For example, starting with water, we can change to acetone, we can change to ethanol or DMSO, a lot of different, even those nonpolar hydrocarbons. So for that case, it's very easy to do post modification for this aerogel. Here we show we can modify the cellulose aerogel by using the isocyanic chemistry. So this is MDI, and then we use the isocyanic group to react with the hydroxyl group, forming the isocyanic group. So polyurethane forming the polyurethane group, right? So here is a before modification, and after modification, the density will increase, as we know. It's indicating that it has been some the MDI has been modified onto the surface. And then we look at the mechanical properties. I show here the mechanical property is increased non-linearly with the density, meaning the modulus, let's say modulus, Young's modulus, as well as tensile, the compression stress. So it all increases with the power law equation, meaning we can make the lightweight material, but also super strong material. So this is by some simple modification after forming the hydrogel. So with the modification of MDI, so we can also turn this into the hydrophobic because the aromatic ring structure in the MDI structure. And then before it was amphiphilic. It can absorb both oil and water. The oil is dyed in red color, the water is dyed in blue color. And after modification, so you can see the water start to beating up. And then so chloroform absorption decrease. The water absorption also decreased to minimum. The reason for chloroform absorption decrease is because increase of the density. This is relative to the weight, how much solvent can be picked up by per mass of the aerogel. And then this absorption can be after modification. It can also be recycled. So for example, the chloroform can be easily evaporated, and then you can use for absorption again. It loses some capacity over the cycles, but if you look at the unmodified one, so it shows much higher. So it after 6 cycles, it only about 30 to 40% of original absorption capacity. However, after modification with a four weight of the MDI, it can maintain much higher, about 60% of the absorption capacity. So meaning this structure become more rigid and more strong, and it can prevent the shrinkage during the evaporation. So those are some of the past work I have been working on the aerogel, and over the past few years, so we also work on the 3D printing. So 3D printing is, especially the direct ink writing, is a very popular material technology for designing the hierarchical structure from the bio-based material, especially those cellulose or nanocellulose, because the cellulose and nanocellulose, they can suspend in water, and then you do not need to use a lot of toxic solvent for processing. Many advantage, as I already listed here. So so here I want to show two examples. One is how we can use a 3D printing to print strong and rigid structure, as shown here. So this structure, this honeycomb structure we printed, it can support over 16,000 its own weight. Here I show as a kettlebell sitting on top of it. And also, can we also do soft and flexible material? Yes, we can, right? As you show here. So this is also cellulose material. We can turn the cellulose material into a soft and flexible. As you can see, it will show very fast recovery after squeezing, both in-plane and out-plane squeezing. So I'm going to walk you through the design of these 3D printing examples. Okay, so first of all, is 3D printing of strong and rigid structure. So this work was done by my postdoc Halai, and also the visiting PhD student Jungang Zhang, and from Beijing Forestry University. So here, what we are doing is we partially dissolve the cellulose using the sodium hydroxide urea system at negative 12 degrees Celsius. So we blend it for 15 minutes. And then here we have different concentration from 1% to 6% of cellulose content. So by inverting the glass well, we can see 1 and 2% they are still flowable. Starting from 3% is can hold to the tube, to the glass well, meaning they are forming the gel. By looking at the XRD spectrum, so we can see the raw material showing cellulose 1 structure, showing the 3 peak for the typical cellulose 1. As we decreasing the amount of the pulp, the cellulose, then we can see there's a more transition to the cellulose 2, right? So here's a peak for the cellulose 2, but we still keep the cellulose 1 peak, especially at the high percent, 6%, meaning there's a partially regenerative cellulose as well as crystalline cellulose. So this is very important for designing the strong material, because we know nature cellulose is very strong because of high crystalline structure. But also we want to regenerate partially. In that case, we can introduce some hydrogen bonding, like also cellulose chain entanglement between the crystalline region, and then we can have the strong materials. So here is some rheological measurement. So for example, we need to show the shear thinning properties in order for the direct ink printing. And also this is storage modulus and loss modulus versus stress. So we can see the yield point. So from here we can get the yield point. So 3% is very low, and 6% is better. So the highest yield point is about 100 Pascal. Is still doable with our injection printing. And then they all show the storage modulus higher than the loss modulus. As you can see here, storage modulus and loss modulus indicating their gelling behavior, hydrogel behavior. So this is a honeycomb structure we developed, and then this is just directly after printing. So you can see this is 4%. Actually, for the 3%, although it shows a good shear thinning and also some gelling property, but it's the viscosity is not very high, and the yield stress is too low. Therefore, after printing, it will be just very easy to collapse. But if you look at the 4% to 6%, this is about 2 centimeter, I think. It's about 2 centimeter tall, so they maintain the structure very well. So 4 to 6%. And then after that, we can regenerate by washing off the sodium hydroxide and urea. So it becomes transparent, it becomes translucent, and then shrinkage, a little shrinkage. And after that, we free dry into this dry structure. So the density of the printed structure is about 80 to 90 milligram per cubic centimeter. Porosity about 90%, and the volume shrinkage will be restricted at higher concentration because there's more materials. But nevertheless, there's about 40% to 50% shrinkage from the original printed structure. So one interesting thing is the structure is elastic when it is wide. So for example, it can be either just after printing, after regeneration. So it can be rolled into, and it can be twisted. So also you can just after drying, you can widen the structure. After absorbing the water, it will become wide, elastic again. So here is showing the after water absorbing, it shows elastic structure. Actually, this inspired the design for the next paper, which I will talk about the elastic structure. But you can see, I want you to notice here, during the squeezing, you see the water is squeezing out, right? So there's a lot of water, and then the water will be absorbed back after it's recovered. So this is a difference between, you will see from the next paper. So here's a cyclic compression and recovery for the white 3D printed lattice. Okay. So as I mentioned, the design for this one is trying to make a rigid and strong material. As I already showed you this picture, it's supporting over 16,000 its own weight. And also it shows a clear honeycomb structure, clear yield point, and then densification, and then plateau region, and then the densification region. So interestingly, I think we saw is 5% is we have the best mechanical property, which is probably due to the balance between the regenerative cellulose and the crystalline cellulose. So we also compare with some other 3D printed. We also compare with other 3D printed materials as shown here. So this structure is shown at the same density. For the 3D printed for the honeycomb, for the foam-like structure, you really want to compare material with a similar density, because it does not increase linearly with the density. So here, so we can see this is compared to those starch foam, MFC starch foam is much higher, or some regenerative cellular aerogel at the density about 100 milligram per cubic centimeter. So we see alignment. So one of the reasons for the strong material is due to the alignment. So we see alignment of the cellulose fibers during the regeneration and during the printing. So this is the color box indicating as a region, different regions. So for example, we see at this region, we see the vertical alignment even at the turning point. So we can still see the fiber is pulling out and aligning along this direction on the toward to the right and toward to the left. So this indicating the alignment of the material. So we demonstrate this one as a thermal insulating material. We know the aerogel can be used as thermal insulating, but the aerogel is in general is a weak material, so it cannot be withhold much higher weight or stress. So here we backfill the aerogel into the honeycomb structure, but for the honeycomb structure, because there's so many open pores, so it's also not a good thermal insulators. So what we did is we backfill the honeycomb structure with the aerogel, and then using the kind of aerogel combine the honeycomb structure as a thermal insulating material. So its performance is I think the performance is falling between a little bit lower than the honeycomb structure, but it's a little bit lower than the aerogel, because there's a lot of solid material that can conduct heat through the structure, but it's still showing the good insulating from both heat and the cold. So here's the temperature change of this is aerogel. Aerogel has a minimal change, and then the filled aerogel with a honeycomb with filled with aerogel, and this honeycomb. So this is the discussion about the rigid and strong structure. So the next one, we are trying to see how we can design a flexible and soft material still using cellulose nanofiber. So the previous one is not exactly cellulose nanofiber because we use a dissolution. We use a cellulose kind of regenerate cellulose method. This one we are using the flexible cellulose nanofiber as I showed from the temporal oxidation. This work was done by Professor Yuan Chen from China Academy of Forestry, who was visiting here for 1 year, as well as a master student Jason Yu. Basically the design here, so we have the 3D printing, and after 3D printing, we cross-link because the temporal oxide, they have a lot of carboxylic group. We cross-link the carboxylic group with calcium chloride, and then by free drying, so we get the material. Because we didn't remove the calcium chloride because calcium chloride is a hygroscopic salt, so we keep the calcium chloride for both for cross-linking as well as for water absorbing. So after that, we can saturate this one into a different environment with different relative humidity, and then it will have the water layer, and then those water layer will trigger the elasticity of the material. So this is because water can serve as a plasticizer for cellulose and for wood. So for example, if you have a piece of wood, if you saturate with water, it will become soft and more elastic. So here we use a temporal oxidized cellulose nanofibers. So we did different concentration at the end. We found 2% and 2.5% give the best printing property. So they show the shear thinning as shown here, as well as the yield strength. The yield point is about 100 Pascal, similar to the previous sample. Then we print a different in-field density. So here is about 20%, 25%, 30%. And then they say after printing, and they say after drying. So you can see they maintain well the lattice structure after printing, after drying. But at 30%, it the printed structure does not see a lot of pores, but you still see pores from the after drying, after remove the water. So here's some effect for the calcium chloride cross-linking. So this one, the SEM image, it shows this one is without any cross-linking. We see a lot of pore structure. Those pore structure is formed by the ice crystal, as we still use free drying to free dry the sample. So a lot of pore structure, and even the holes is barely to be observed. And then if we cross-link with 0.1 molar calcium chloride, so we can see the structure become more compact. This is because during the cross-linking, the fiber can be brought close to each other by the calcium chloride. And then with the 1 molar calcium chloride, so we can see the structure, all the pores has been removed, and this structure showing a very dense and well-defined printing lines. And then if you zoom into here, you can see there's a large calcium chloride crystal here. So those are the residual calcium chloride, which will be used for the water absorbing. We compare with water absorption with the ash content. Ash content, basically we burn off all the organic matters and then leaving only the inorganic, which is calcium chloride. So we can see the ash content is a proportion to the water uptake. Or the water uptake is proportional to the ash content, meaning so its majority is the water absorption is due to the calcium chloride. So we know the cellulose is a polar polymer, so it has a lot of polar function group. So we look at the this one is without any cross-linking. So we look at the water uptake of the printed cellulose. So it only absorbs about 5 to 7% is minimum water absorption. As we increase the calcium chloride content, so we can significantly increase the water uptake. And for this one, the 2 molar calcium chloride, so we can increase to about 80% water uptake. So this is I believe this is 43 relative humidity. And then we look at the ash content with different calcium chloride, so it's still the same thing, proportional to the water uptake. And then we also did different 43 up to 95% of the relative humidity. What we can see is there's so for the water uptake at 95%, so after 25 hours, it can saturate about 200 2.5 times of its own weight, meaning there's a lot of water absorption in there. But remember, I asked you to remember what it looks like for the whited 3D printed structure from the previous. When you compress, it will release the water. But for this one, so if you compress, it will recover. So this is a in-plane and out-plane compression. So you can compress it, and after that you can release it. So it will recover to the original state, but also it does not release water because all the water are bonded water are now free water. So those are now going to be so the calcium chloride absorb water. Those water will be bound by the polar group on the cellulose. Therefore, it still feels like a dry material, a little bit white, but it's not going to be feels like a soaked sample. So we did the compression testing, both in plane and out plane, for different for over 100 cycles. So you see it's very fast responsive. I think the speed has been increased to 8 times, I believe so. It shows hysteresis, meaning there's some structure breakage, but it's still those hysteresis, meaning there's energy absorbing. So it can also be using as an energy absorbing form for example, for the car component or for some other where you need where you are expecting some shock. So because there's a calcium chloride in there, and also there's water in there, although the water is free water, it's not it's a bond water, it's not free water, but it still can facilitate the ionic the ion transport. For example, here we have calcium chloride, calcium cation and the chlorine ions, and then it will be serving as ionic conductor. So we have this home design of this instrument, and then it shows it can, as we increase the strain, so there's a difference of the resistance change, meaning it can be serving as a stress sensor. So for here we have, and also because it has very good shape recovery, so after releasing the strain, so it can go back to the original state. So there's 7% strain, 14% strain, and 15% strain. So in all cases, it can immediately recover to original state, and then you can do multiple cycles. Okay. So those previous are the discussion about the hierarchical design for the aerogel and for the 3D printed structure. So starting from here, so there will be I will discuss some applications. So for example, electronic, environmental, and energy. So very briefly, so those are some work we have been working on. So environmental, for example, antibacterials. So we can use a cellular nanofiber to synthesize a silver nanoparticle. The silver nanoparticle can be serving as interesting. So for this paper, we are seeing it can serving as a mop to collect all the bacteria. So this is very interesting. It's not only kill the bacteria, but also collect all the bacteria. So for this one, the wood structure can be decorated with platinum nanoparticles and serving as a catalyst for water treatment. And also this, we also synthesize a triangular shaped anisotropic silver nanoprism, which can use for the Raman surface enhanced Raman scattering. Or the aerogel most often used is for the water treatment, for example, oil water separation by absorbing or by filtration, as well as solar steam generation, as well as dye removal. And some work on the energy management or energy storage. For example, the nanocellulose can be used as a solid state electrolyte for the lithium ion battery. If you carbonize the aerogel, if you carbonize the cellulose, it can be used for the supercapacitors as a carbon. And also thermal insulation, which is typical application for the aerogel. So this is very brief discussion about the solar steam generation. So here's we are using the cellulose nanofiber aerogel as a foam, this white foam. So because the cellulose is a white material, so it does not interact strongly with solar energy. Therefore, we coat the surface with a layer of the carbon nanotube. So the carbon nanotube after coating, so the layer is black. So this can serve as a black absorber, solar energy is absorbing, and then those pore structure can serve as a water transport. So those are the absorbance data. So from the in the visible to the near IR range region, so we can see that the surface for the CNF CNT is showed over about 100 absorbance, and for this one it's very low absorbance in the visible and the IR region. Therefore, so this is more effective in converting the solar energy into heat. So based on the temperature, so you can see this coated under one solar illumination, so it's about 32 degree, and the uncoated one is only about 23 degrees Celsius. So you can further increase the temperature by increasing the solar illumination power. For example, 10 solar energy. This is in general, we have one solar energy, but if you increase to 10 solar energy, you can increase to 100 degrees Celsius. So we demonstrate the solar steam generation with evaporation rate. So compared to the coated and uncoated one, so the coated one showing the enhanced factor about 4 times, 2 to 4 times. And the efficiency for the light to heat to the heat conversion is about 80%, which is very high utilization of the solar energy. And also this kind under one solar, we also demonstrate over 50 cycles. So it can be maintained a stable evaporation rate about 1.1 kilogram per square meter per hour. So this was done a couple of years ago. So for 4 years ago, I'm sure right now the efficiency has been improved, and also evaporation rate has also been improved. So we are currently working on some other design in this area in the lab. So hopefully we will have more update in the future. So this is a removal of the dyes. So we know there's a lot of dye pollution, for example, jeans, dyeing the clothing, dyeing the jeans. So there are a lot of dyed water. So we use the cellulose aerogel as a dye removal. So the cellulose nanofiber, we know it has a negative carboxyl group. And then we use it, therefore we use it for removing the catenate dyes. For here, we are using the Melichin green. So other than using the surface function group, we also create those mesopore on the film. So here's a free dried aerogel, and then we create those mesopores in order to increase the contact with the dyes and also increase the surface area. So we show very high dye absorption. So from the long mule, we feed both long mule and the front leg. So the long mule is basically showing the better filling. So the maximum absorption capacity is about 212 milligram per gram, so which is very high. And also this can be regenerated. This one is show the removal percentage. So we can have depending on the dye concentration, so we can have very high removal percentage if we have lower dye concentration. For example, this is a ratio between the aerogel and the water. So starting from 100 milligram per liter dyes. And also we can do repeated utilization of the aerogel, and then this is 10 milligram, and then after 5 times, so we can completely remove the color from the solution. So the dye can be removed by just using by changing the ionization, which I didn't show here. So for example, after being saturated by the dye, so you can just use the salt water because the salt water increase the ionization can screen off the chart, so to break the electrostatic interaction. So it can be very easily to regenerate by just using the sodium chloride solution. So this is another example we are using for the water. This is not water treatment. This is more like a water detection, water contaminant detection. So as I mentioned, so we can use cellulose nanofiber to synthesize those 3 nanometer silver nanoparticles. And here the interesting part here is we are using combined oxidations and reduction. So we have the sodium hydrogen peroxide as an oxidant and the sodium borohydride as a reductant. So by combining those at a different ratios, then we can convert this into those anisotropic triangular shaped silver nanoprism. And then from here we can see we can get a different color because they have different plasma resonance peak. As you show here. So here is the original spherical nanoparticle is usually about 400 nanometer. By changing those into the anisotropic nanoprism, so we can cover almost the whole spectrum of the visible range from 400 up to 800 nanometer. So we did some explanation for this one because the interaction between the silver atom and the surface of cellulose is through the carboxylic group. So we did some calculation based on the we assume the 36 chains and also the triclinic crystalline allomorph. So we calculate roughly the distance between the different carboxylic group, and then we also calculate the distance for the different facet of silver nanoparticle. For example, here's 11100 facet, and this is 111 facet. So for the 111 facet, so we can if we pick out the different chains, we can actually see the distance matching to this distance much better. For example, 0.992, and this is 1.03 nanometer. So therefore, we assume the carboxylic group will be the cellular nanofiber will be preferably absorbing onto the 111 facet in contrast to the 11100 facet. What happens? So if there's no cellular nanofiber in there, it will be the silver nanoparticle will grow isotropically. It will grow into a spherical, right? It will grow into a ball. But if there's a cellular nanofiber, for example, this is silver, if the cellular nanofiber is attaching onto here, onto the 111 facet, then the 111 facet will now be able to grow, continuous growth. Therefore, it can only have the lateral growth, right? So therefore, we are expecting we can see the 111 facet from the XRD, which we did for here with the XRD shows there's for the silver nanoprism, it shows very strong 111 facet, meaning that facet is still exposed, it's not grow with the other nanoparticle. But for the spherical, you can see mostly the intensity is not high because we don't have a lot of materials in the film. But you can see it shows all the 100 facet, all the facet you can have. And then for this one, we are using for the water contaminant detection. Here we are using Rodman 6G as a model toxicant. Here we have the silver nanoprism and the different concentrations of silver nanoprism and the silver nanoparticle we call silver nanosphere. So for the silver nanosphere, even at 5 times 10 to negative 4 molar concentration, we couldn't detect any peaks. But for the silver nanoprism, we have half of the concentration, 10 to negative 5, we see very strong peak. And then based on here, we can get the apparent enhancement factor, which is about 6,000, 7,000 enhancement. So meaning you can use this to detect trace chemicals in the water body, right? So this example I want to discuss is about anti-folding and antibacterial cellulose membrane. This is was done by Dr. Chen, was a postdoc here. So basically we are just doing the ATRP reaction onto the surface of cellulose membrane. So we have cellulose membrane, so we grabbed with the BIBB as a user esterification reaction, and then grab the DAC and the SBMA, which the DAC contains a quantum amine group, and the SBMA contains is a twin ionic structure, contains both quantum amine and also sulfonic acid. After grafting, so we demonstrate it has the membrane can be easily converted into anti-folding and antibacterial. This is anti-folding properties. We use a different protein, negative charge and positive charge, BIC and lysine. So basically CM1 and CM5. CM1 is all DAC. So for example here all quantum amine, and then the CM5 is all PSBMA. So the PSBMA gravity because it has a higher water affinity, therefore it has lower protein absorption. And then the antibacterial, we did both gram negative and gram positive, equalize those as aureus. So it shows both for the CM1 has the best antibacterial property because it has higher density of the quantum amine, but this one is CM5. It also has decent antibacterial bacterial reduction. This is SCM after this is a modified one. This is a modified one, so we can see there's a significant reduction of the bacterial adhesion as well as compared to the original one. So also it showed very good cell viability. So by incubating the fibroblast cell so into the extract, so after 5 days, they still see very high cell viability, which is the fluorescent dyed into the green color. So there are a couple of dyed cell red color, but even the control they have some dyed cells. Okay, so next one, I'm going to just share the thermal insulating aerogel. This was done by Mingyao Song, was a master student, recently graduated from the group. So basically, cellular nanofiber aerogel has been used for the thermal insulating materials, but the thermal conductivity is not very high. It's not very low. I mean, it's about 25. I would say about 25, 20 to 25 milliwatts per meter per Kelvin. So my challenge to the student is whether we can do reduce the thermal conductivity. So what we can do. So based on the thermal conductivity, so there are three parts: the conduction, the convection, and also the radiation. Okay? So for here, so because the cellular aerogel we are producing is mostly open pores, so then we think what happens if we make those into closed pores? By having the closed pores, it can be reducing the convection, reducing the airflow in the aerogel. So what we did, I will just quickly go through. I think it's kind of running late. Quickly go through. So we use oil in water picking emulsion. For example, here is we use a hexadecane oil in water. So the particle size about 1.3 micrometer. And then after we got the emulsion, so we can mix with different ratio of the cellular nanofiber suspension. This is without emulsion, so it's so transparent. And this is with different content of emulsion. This is 2%, 20%, 40%, and up to 100%. It shows the milky white structure because of less scattering. And after that, we can use the solvent exchange to remove the oil inside of the emulsion. And after remove the oil, so it becomes transparent. We use the acetone to remove the hexadecane. And then there's a volume shrinkage due to here. They start from the same height, the same diameter, but after that you can see the without the emulsion it shrink a lot, and after with the 10% with 100% emulsion, there's a much higher volume retention. This is because if you have a spherical in there, the sphere will be resisting the stress, right? So during the evaporation, during the drying, so during the solvent exchange, there will be stress induced in there. So therefore, the spherical will be reducing the stress. So we use a confocal we dye the structure, and we can clearly see there's a pores in there, right? So they said the original without any emulsion, they said 20%, 10%, 100%. So there's a lot of pores in there. The pore size is also about 1.4 nanometer, 1.4 micrometer, as measured from the microscope image. So this one we can do the free drying. So we can free dry. So basically what we have here, we have the all fiber cellulose, all fiber aerogel, which is shown here. And then we have the entangled fiber entangled with a microsphere aerogel. So the density about 20 and to 10 milligram per cubic centimeter, because this has better volume retention. The starting have the same concentration, but because it's a better volume retention, therefore it has a lower density. So from the ICM image, we can see. So this is the original cellulose nanofibers aerogel without emulsion. So you see those open connected pore structure, those mesopores, and by including those emulsion in there, we start to see some closed pore, right? So the pore will cut open, but you can see it's closed on the other end. And they say 80%, and they say the 100%. So you can clearly see very similar to what we have for the polystyrene for you know, those polyurethane polystyrene foam, right? Closed cell foam. So it's very similar, but also the pore size is much smaller. This is 10 micrometer scale bar, and then this usually is about a millimeter range. Okay? So we actually, by using this method, we are creating those closed pores. We call it quasi-closed pore because it's not all pores are closed. Some pores are still open because it's hard to control everything closed. And then by looking at here, so you can definitely see those embedded pores in here, right? So we did the pore characteristic using a BT surface area. So for example, for the the same color is emulsion without emulsion is a pure cellulose nanofiber aerogel. So it mostly shows on mesopore, right? So which is clearly see from here, those networks structure about a few hundred 20, 50 nanometer pore size. But after here, we see there's very small mesopores, even micropores, we'll say. So this is because on the pore wall, so they generate a lot of small pores in there. So the material is still flexible. So as you can see, it can roll, and the mechanical properties increase as we increase the emulsion concentration, and then it decreases because there's not much interaction. But if you look at the spacing modulus, it's always increased up to 80% of the emulsion. And then we did the conductivity because we want to see how it can improve the conductivity, right? So reduce the thermal conductivity. Starting from here, we have 22 milliwatts per meter Kelvin, and then by having the 80% and 100% aerogel, we actually can reduce it to 15 milliwatts per meter per Kelvin by having those emulsion, by having those close pores in there. So the last example I want to give to you is ionic conducting cellulose nanofiber PVA organohydrogel. This was done by my PhD student, third year PhD student Yu Hang Ye. What we are doing here is we are using the cellulose nanofiber to incorporate into the polyvinyl alcohol hydrogel, and then there will be forming the network structure between the PVA and also the cellulose nanofiber chains. And also we use a binary solvent system, DMSO water, which can introduce not only the shrinkage of the structure to make the structure more condensed, having the nucleation for the PVA, but also it will introduce the anti-freezing properties. Also, we have the sodium chloride in there serving as the ionic conducting species. So very interestingly, by adding the cellulose nanofiber, even by adding 1% cellulose nanofiber, so we see it dramatically increase on both the stress and also the strain value. So this is a modified one, this is the original one, this is 1% and 2% and 4%. So it start to decrease the strain, but also the stress is continuing to increase. I mean, increasing the stress is very common because cellulose nanofiber has a high crystalline structure, but increased strain, especially at the very beginning, is very interesting, indicating there's a strong interaction between cellulose nanofiber and also the PVA. So we look at the toughness. The toughness also reach the highest toughness, which is area below this region, the tensile stress strain curve. So we can improve the toughness, and the toughness start to decrease a little bit at 2% and 4%, but it's still much higher, more than 2 times of the or 3 times of the original PVA. So the hydrogel, organic hydrogel, it showed transparency. It showed very good stretchability as well as compressibility. I show here. So we introduced different amount of sodium chloride in there. For example, 0.05 molar to 2 molar. As we increase the sodium chloride, the conductivity, ionic conductivity increase. This is a no, but we also see that by increasing the cellulose nanofiber content, we can also improve the ionic conductivity because 2 reasons. So one is it can introduce some of the pore structure, hierarchical structure in there for the ion transport, as well as a surface carboxylic group of the cellulose nanofiber, which can facilitate the ion transport. So we compare with some other polymer hydrogel. For example, we know the ionic conductivity and the mechanical property are dilemma, right? So mostly for the high ionic conducting hydrogel, it's usually very soft. For example, polyacrylamide and alginate. So those are very soft material and it has high conductivity. But if you have very strong material, for the gelatin or PGDA ionic liquid, and then this will be low conductivity. However, we are achieving both high conductivity and also high mechanical property as here. Although the target here, but we believe we are making some improvement to the current literature. So it shows ionic conductor. So the conductivity change or resistance change at due stress. There's a longer transporting distance, the increase in resistance, and the light bulb become darker, and then by compressing, you are making it more conductive. So freezing. So the goal for this one is to prepare anti-freezing. So we know we mentioned we use the DMSO and the water binary system. So for here, for this organohydrogel, it still showed very good flexibility at negative 70 degrees Celsius. But for this one, hydrogel, it break into negative 20 degrees Celsius. So this is very useful. For example, if you like outdoor, if you like the skiing or something, you go to the mountain, so it can still working. Right? So for those conductors, so the conductivity will reduce as you reduce the temperature, which is obviously, but it can still light the light bulb even at negative 70 degrees Celsius. Some demonstrations, some of the stress sensor and the compression sensor. So finger and also even it can detect very subtle change, for example, pulse and also speech. Very excellent researchers in the lab and hardworking as well as innovative. So without them, so those now those work can be done. The work I highlight including Dr. Chen. Dr. Chen right now is working in Westlake University in China, and Halai is a postdoc in my group. And Professor Yuan is celebrating the birthday and in Chinese Academy of Forestry in Beijing. And then Jungang and Yuhang was Jungang, Yuhang is here, and then Mingyao has already graduated, and Zhen Yang, Jason, Ivan was here, and Zhen Yang is here. So now I don't have time to include everybody's work, and because there's still a lot going on in the lab, and so hopefully we will share this later. And also thanks for the collaborators and in UBC and globally. With that, I would like to thank the Asian Pacific Network for forestry restoration and rehabilitation for the invitation, and also the AP Asia Pacific Forestry Education Coordination Mechanism as a University British Forestry, Effective Forestry for having this excellent event. So I'm very, as I mentioned, I'm very honored to have this opportunity to present the research. And also some funding agencies, Ministry of Forestry, those kind of research here, NSERC and National Defense. With that, I would like to thank you all for your attention or for attending this seminar, even though I know in Asia right now it's a Saturday morning. Thank you for spending time with me. And if you have questions, you can let me know. You can just send me an email if you have questions. Thank you very much.
Okay, thank you. Thank you very much, Professor Jiang, for this excellent talk. So actually, I saw some questions in the chat box. So yeah, so maybe we can answer some of them.
Okay, let me see. I think I can see the chat box. Let me see. Yes, there are many excellent work in wondering. Okay, yeah, so excellent work from, I'm wondering what is the effect of carboxylic group content of, no, I cannot see the whole question. Let me see.
So
on the cellulose alignment during the 3D printing. Yeah, so thanks for your question, Dr. Hu, Jingguang Hu is my best friend, working in the University of Calgary. This is a very good question. So my answer is we haven't investigated the effect of the carboxylic group. So I think so there are two effects. So right, so one is the carboxylic group. It can be have some repulsion. So that's why you can disperse the carboxylate nanocellulose into the water. But also it can form a strong hydrogen bonding because it has a more polar group. It has carbonyl group and a hydroxyl group. Right? So I think the alignment is mostly due to the shear shear force induced by the nozzle. But I think yeah, I don't have an exact answer for this one, but I think that might worth to be investigated. Thank you. We have another question. Can you introduce some normal method to prepare cellulose-based hydrogel and aerogel? So the normal method, so currently there's a lot of way of preparing the cellulose-based hydrogel and aerogel. So you can start from different material. For example, regenerate cellulose. You can start from the cellulose in different solvent on the liquid, right? So you can regenerate them, and you can make the hydrogel. And also, as I mentioned, you can start from the nanocellulose. The nanocellulose starting from the aqueous suspension, depending on the surface chemistry. For example, if the surface chemistry is carboxylic group, if there's carboxylic group, I think many people are using the, for example, divalent or trivalent chitin to cross-link them. Another way is my colleague here, Emily Krasny, I think her way was introducing some covalent linking between the cellulose nanocrystal. So I think there are many different ways. So the way I'm working in our lab, we don't want to use a lot of chemical cross-linker. So therefore, we only try to harness the surface chemistry of the existing nanocellulose by using the freezing thawing method. So this is what I introduced in the previous aerogel section. Yeah. I hope this answers your questions. Okay, let me see. Thanks for your good question. It's a very interesting topic. So the question is, I was wondering if you have studied the effect of cyclic compression test for longer period of time. I mean, can we keep the structure integrity if we compress it for 1 hour and then load and reload again? We didn't hold for a very long time. I'm sure for those elastic material, I'm sure it can recover even you hold it for a longer time, because I don't think you can break the internal structure. It definitely can still hold. And for yeah, so this we didn't done, but we didn't do. But I also so for this one I didn't show here. So I also run a car onto the aerogel. So by running through the car, it can still recover. So it indeed show very good recovery properties. Okay, the next question, can I ask a question about the preparation of CNC and CNF? I wonder why sulfuric acid destroy the amorphous region when we prepare CNC, but the temporal system destroy hydrogen bonding between the cellulose chains when we prepare CNF, as you show in the picture. Sulfuric acid is the most common way for making the cellulose nanocrystal, and because it has very strong acid, and then the ether linkage between the glucose chains can be very easily to be broken. So that's why it can be removed. It mostly focuses on the cleaving the 1,4 glycosidic linkage, right? So by having that, and also the amorphous region, it has more accessibility for the acid. Therefore, they can access to the amorphous and cleave out the amorphous region. For the temporal oxidation is just the simple mechanism. Is a temporal oxidation is a selective converting the surface carboxylic group, surface hydroxyl group, the primary hydroxyl group into the carboxylic group. So in the cellulose elementary fiber, the hydrogen bonding is mostly formed by the hydrogen bonding between the interfiber hydrogen bonding. Therefore, by converting those primary hydroxyl group into carboxylic group, which has a negative charge, those negative charge will be repel each other and facilitate the breaking into the nanofibers. Yeah. So I think there are a lot of review talking about the temporal oxidation and the sulfuric acid hydrolyzed cellulose, and hopefully you can check some online. So it's just my very brief answer. Okay, let me see. I have Jen, Dr. Zhou from Zhongshan University. Thank you for attending. It's possible to get perfect closed cell by emulsion templating. It's not that. I would say it's not really achievable, because for the emulsion templating, the oil in the core need to be exchanged, right? So there need to be have some like a porosity for example, the hexadecane in the emulsion need to be exchanged by the acetone. So I think in that case, it has to be so some pores will be broken. And even if you look at those commercial polyurethane or expanded polystyrene, so they are not perfect pores. So I think this could be yeah, so something to worth trying, but it will be very challenging if you want to maintain all the pores. So now are we continue or what do you think? So I know we are running a little bit longer.
Yeah, sure. Maybe just two left, or maybe if you don't mind, just address all the
Okay.
questions.
Yeah, I'm okay. So I just yeah. So I think there's still a couple questions. So let me try to answer those questions. Can you introduce how prepare the Pickering emulsion in your work? The Pickering emulsion is well studied for nanocellulose, either cellulose nanocrystal and cellulose nanofiber. So the one we are here is we have the we use the hexadecane as an oil layer, and then we have the cellulose nanofiber in the as a aqueous layer. So we use the sonication for different amount time. So you can check the you can if you didn't get the literature, you can check the literature. I think it all describe the ACS applied materials. So you can check this one. It's all included in there. So just basically sonication of the oil with the present cellulose nanofibers. Okay, one question. Have you tried other solvent in addition to sodium hydroxide urea during the DIW? This one has not been done. We do work in the lab with some other cellular solvent, but it's not for the 3D printing. Yeah, I think maybe some other people there's some literature in there to have done the sodium hydroxide, have done other solvent, but the purpose of this one, we don't want to completely dissolve the cellulose. Therefore, we choose the sodium hydroxide urea because we found it can, by controlling the time and by controlling the condition, we can partially dissolve the cellulose. Right? Can I ask a question about the anti-fouling membrane that can be used in absorption or filtering for the antibacterial membrane we are preparing is now for filtration. So it's so the probably it will be used for packaging because it's very dense film. There's no pores in there, so therefore it cannot be used for the absorption or filtration. So but but the technology, I mean the ATRP surface modification can definitely done with so it can be even done with filter paper, right? So you can do the filtration in that case. Okay. Okay. So I think there's still a couple more. What do you think? So
yeah, so it is like maybe pick the last question. So for all the other audiences, if you have any question, you can maybe email Professor Jiang to discuss about it. How about it, Professor Jiang? So
yeah, so you can send the question. If you have question, you can send to my email. I hope you can see the email. Let me just do a one question. So battery. So let me see the last question. I'm a PhD student at UBC and work on solid state battery. My question is the thickness of your cellulose membrane controllable? Okay, so if you are at UBC, welcome to send me an email. I'm happy to discuss this. Okay, so yeah, thanks Orlando. I didn't know you are here. Thank you for joining.
yeah, thank you, Orlando, for
All right,
joining.
I think that's all. Yeah.
Okay, yeah. Thank you very much. I guess like maybe it's the time to end today's session because I don't want to keep everyone very late, especially from the Vancouver side. Yeah, and also we are very happy to have Professor Guangyu Wang here, and who is the Associate Dean of Faculty of Forestry in UBC, and also the Director of the AP-FECM Executive Office. Well, Professor Wang, would you like to some like closing remarks?
No, I just want to thank Professor Jiang for the excellent talk. And thank you for everybody to join our event. Thank you.
Yeah, thank you. And maybe here I would like to give everyone a short notice that in about 2 weeks time, maybe I'll just quickly share my screen here. Yeah, in about 2 weeks time, the same time we will have Professor Mark McLaughlin from UBC Department of Chemistry to deliver his talk, which is titled the Creating New Photonic Materials from Cellulose Nanocrystals. So please feel free to register the talk via the same link we shared before, and also we will share the Zoom link for that session later with everyone. Okay, so that's all from today. So thank you very much for joining us today, and have a good day from Asia side, and also from have a good night from Vancouver side. So thank you very much, everyone.
Bye-bye.
Thank you.